All right, hello, the show is back on. Today is about to be day 6, relearning number theory and proofs. I just wanted to show very quickly what we did yesterday and just summarize before we just jump right into it and start doing some proofs and working through a couple of exercises. So, if it's your first time seeing this, hello, my name is John. I call myself the math hobbyist. I studied pure math 15 years ago and got a degree and decided not to do graduate school. Now I am relearning mathematics as a hobby, but it's a deep hobby. It's what I like to call a deep hobby that I'll pursue the rest of my life. So yeah, this is a practice stream. Everything is going to be a little impromptu, a little not polished, and again, I am not a professional, so please do not expect professional level mathematics here. This is a hobbyist stream, but I somewhat know what we're doing. We are doing number theory this week. We're working through this book by George Andrews, and we are doing this book by Velleman. So I'm using How to Prove It in order to show mathematical proofs to people who might be seeing it for the first time. And I'm also practicing how to teach mathematical proofs and teach stuff that I already know really well. I think that teaching is an important part of learning anything. And I never learned that. I never did that back in the day when I was in my first time around trying to learn math. So now I understand how important teaching is. So we're doing number theory. Yesterday, I just gave like a quick little intro to proofs, and I talked about like the organization and the human definitions of lemma, theorem, corollary. I introduced how math is a logical, structured, axiomatic system, and I gave this canonical proof. It is the proof that I was going to show myself as like, here is what I consider a great introduction to proofs. A theorem by Euclid, there are infinitely many primes. I gave my proof of the theorem. Then I gave a little bit of self-criticism after we worked through it. In particular, I noted that I don't think that the proof needs to be a proof by contradiction. I think you can call it a proof by construction. And yeah, so a little bit, I did my attempt, and then I reflected a little bit, and then we moved on, and I wrote out verbatim what Velleman's proof was. And I was very pleased to see that this was theorem number 1 in Velleman as well. So this is like the most loved book on how to learn proofs, and he also chose to show Euclid's infinite primes as the first thing. His proof is a little bit wordier, so I gave some reflections on what I thought about style, and I talked about how different proofs, like the same proof, the same theorem, will have a very different proof according to different authors, and that depends on the audience. Like always when you're teaching something to somebody, you need to keep the audience in mind. Right now, these videos, I'm trying to shoot for a wide audience, including people who have never seen pure math before. But over time, we may try to scope down and like target a little bit more to people who have seen pure math. Please let me know in the comments what you would like to see. Would you like this to be targeted to math majors, to graduate students, to people learning it for the first time? Right now, I think we have a good blend of people, and I like that aspect of this channel. Anyway, so we did Euclid's infinite primes, and then we worked a couple of problems from Velleman. This one was cool. Use Euclid's method to construct new primes from a list. So, as I said, Euclid's method is really a construction to find new primes. I struggled for a moment and then realized, oh, wait a minute. Because I've tested all the primes up to the square root of 211 and none of them were prime, or none of the primes up to the square root of 211 divided 211. Therefore, I know 211 is prime. So using Euclid's proof, 2, 3, 5, and 7 generates the prime 211. And then 2, 5, and 11, that list generates the prime 3. So the product that Euclid defines itself does not need to be prime. And that's an important thing to remember. It's a common gotcha amongst people learning that proof for the first time. Then we did Velleman 1.1.6. I will buy the pants, I will buy the shirt. And I wrote out what these symbolic expressions mean in English. Then 1.2.1, we solved that exercise, introducing truth tables very quickly, and I wrote out the truth tables for these two statements. Cool. So let's jump into it. I see we have one person. Hello, how's it going? We've got already one person watching in the chat. That's fantastic. All right, so this, I forget what I just said, day 6. I'm a little too neurotic on this. Like, I want to write down the right day. What day is it? Day number 6. Day 6, relearning number theory. Oops. Day 6, relearning number theory, parentheses, and proofs. So this series is where I want to talk about proof-based mathematics and learning how to write proofs. But I'm not going to reiterate that all the time. I'm just going to say relearning number theory from here on out. Okay, and then 2 videos ago, I wrote out a path. I wrote out 2 videos ago, I wrote out a path, and I stated one of the goals. Long-term goal is right here. Long-term goal, understand Fermat's last theorem. That is an ambitious goal. That's like saying I want to climb Mount Everest. It's good to shoot for the moon, and we'll get to some really cool stuff along the way, even if we don't get to the top of Everest. In the nearer term, one of those treasures that we're going to get to along the way is Gaussian reciprocity, quadratic reciprocity. Following that, someday we're going to get to odd versus distinct partitions by Euler. Those are 2 beautiful gems that we want to get toward. And even before those, I'm going to draw a little arrow here. Before those, we're going to visit the fundamental theorem of arithmetic. And so, the fundamental theorem of arithmetic proves that we can do that long division algorithm that we've all learned in elementary school. We all learned how to do long division. And the fundamental theorem of arithmetic kind of proves that every number has a unique factorization into primes. So some of us know that, or we've all learned that at some point, and we're going to prove why that's true. It's not obvious that every number can be written uniquely as a product of primes. So, yeah, that's what we're going to get. I wrote down every theorem along the way in the journey to the fundamental theorem of arithmetic, and I wrote down every theorem without proof. So today I want to get through the proofs of one of those. Maybe I'll just copy verbatim without fully understanding the proof of Theorem 2.5, the actual fundamental theorem of arithmetic. So I'll just memorize, just practice writing down the proof of that. But I do want to get through the proof of probably, I want to see the proof of Theorem 1.7. This one, this is going to be a target for today. I've already, on my own, done the proof for Theorem 1.1, the formula for triangle numbers. But I think today would be a good day to see a mathematical induction proof, just to repeat that information. What does mathematical induction look like? A proof by induction. And so I think that we'll do the proof for Theorem 1.7 and fully understand it. We'll write down the proof for Theorem 2.5 and not fully understand it. And then we'll probably do an exercise as well. So, join me, everybody. What do I need? I need to copy. I want to copy this statement so that I don't have to rewrite it. Oops. One more time. I want to duplicate that, and I want to get a copy of that along with the fundamental theorem of arithmetic. Let's get both these. How's it going? Today, understand proof of 1.7. Is that 7? No, that must be 1.2, I think. I'm going to say copy and then finally solve an exercise. I don't know which one yet. I think I want to do those in that order. So skip ahead if you're more interested in seeing the proof of the fundamental theorem or solving an exercise. Yeah. And why don't we take a quick moment to say, please hit the like button right now. If you enjoy this video, if you're still watching and you enjoy it, please hit the like button. It really helps so much, especially as a brand new channel, so that we can tell YouTube that this kind of content is cool and that it should show more people what pure math looks like. So let's jump into it. What color do we want to use today? I think the cyan is always nice. Theorem, I believe that this is 1-2. All right, so if x is any real number other than 1, we have the sum of 1 plus x squared, x to the n minus 1 is x to the n minus 1 divided by x minus 1. So I'm going to try it on my own before I read the proof from Andrews. This is very good practice for me. So skip ahead if you just want to see Andrews' proof. Just for fun, let's say that Andrews is this nice bluish color. I'll be yellow. And this may be completely wrong, so please forgive me. Don't learn from me. Okay. So I have not read the proof yet, but we're going to do this by induction. Base case is clear. You know what? We don't need to be demeaning or anything. Base case is satisfied as let's see, if as n equals 1 has the sum j equals 0 to 0 xj. So the only term in this sum is x to the 0, which is 1, and 1 equals x to the 1 minus 1 divided by x minus 1, right? For any x not equal to 1. Those two terms cancel out, right? So we see that the base case is satisfied, but at the same time, just for intuition and just to see that this works, I want to write out the table for a few cases. Because in the real world, this is what you would be doing. You would see a bunch of evidence, like computational examples that something is true, and then you want to see, can we prove it, that it's always true? So we've just shown that I'll write the summation symbol to just mean the left-hand side of the equation, and then I'll write out the right-hand side correctly. X to the n minus 1 divided by x minus 1. I suppose we would need a value for x. Let's take x to be 2, just forever. I don't know, just to have an example. Then the summation would be when n is 1, again, we only have one term, 2 to the 0. This one would be 1 plus 2 to the 1, which is 3. The next term would be 1 plus 2 squared. That's going to be 4 plus the last term, which is 7. Then we have the last term plus 2 cubed, which is 8. So 8 plus 17 is 15. And then let's just get one last example. 15 plus 16 is 31. Okay? When n is 2, when n is 3, when n is 4, when n is 5. This is not a proof. What I'm doing right now is more just giving a concrete example of a mathematical statement. And this is very important. Examples are important. Don't skip the examples, because seeing examples helps build your mathematical intuition, even if it's not, quote-unquote, the mathematics. I don't know. All right, so then the right-hand side, when the right-hand side is 2 and n is 1, then we have 2 minus 1 divided by 2 minus 1 for the first term. We have, I'm going to erase all this stuff on the left, just the scratch work. When n is 2, then we have 4 minus 1 divided by 2 minus 1, right? That's 3 over 1, and indeed that is 3, as we expect. Then we have 2 cubed minus 1 divided by, so the bottom term is always going to be 2 minus 1 for the value of x that we chose. So that's nice. We can really only care about computing the numerator. Okay, so 8, yeah, we see that this pattern is working. The next term is 16 minus 1, 2 to the 4 minus 1, and then, yeah, that's 15, and then this one is 31, and then the next one's going to be 63, and then the next one is going to be 127, because those are the powers of 2 minus 1. All right, so I think that's enough. I think that's enough right now to feel some intuition that this thing is true, and we have this cool fact in the world that we want to see is always true. I think that's neat. I think it's worth showing concretely a few examples to have some more motivation to learn why. Like, why do I care about this formula? Like, that's a cool identity, I think, and it can be useful in other proofs. But the only thing that matters is this case. Really, this one is true for any x not equal to 0. We just assumed x is not 0, and then we proved that the base case works. When n is equal to 1, mathematical induction is like dominoes. First, you show that you can tip over the first domino, the first base case, and then you show that anytime that the proposition is true for one domino, that it's also true for the next domino. That way, you tip over the first one, and then you've proved that every domino is close to the previous one. Like, every 1 implies 2, 2 implies 3, 3 implies 4, on and on forever for all numbers. If you prove those two steps, then that is a proof by mathematical induction. All right, so let's move on. So we see that the base case is satisfied. Now assume for some n greater than or equal to 1, we will show that the proposition for the next number is also true. Okay? Then the left-hand side is this. J equals 0, and then here, the left-hand side has j equals 0 to n minus 1. So then the numerator is then n plus 1 minus 1. Or let's just more quickly write j equals 0 to n, x to the j. Well, we can split that summation as j equals 0 to n minus 1, x to the j, plus the next term, when j equals n, then we have these two terms. And by hypothesis, we assume that that this proposition was true for the prior case. Then this is x. What was it? X to the n minus 1 divided by x minus 1. And then we're adding the following term. This is called the inductive hypothesis. And so now we've got, just by some algebra, this step here requires the fact that x is not equal to 1. So does the prior step, because it already used this division here, but the step where this algebraic rewriting and the fact that x is not equal to 1 allows us to rewrite that second term. Now they have a common denominator, and we have x to the n minus 1. So I'm combining the two terms, x to the n plus 1 minus x to the n. Okay, divided by x minus 1. So let's rewrite this a little bit. Oh, look, x to the n cancels with that x to the n, and now we have x to the n plus 1 divided by x minus 1. And that's what, which is the, which is the equation we wanted to show. I don't like that. I don't like that phrasing. I don't like that. I'm going to say, therefore, the left-hand side equals the right-hand side from j equals 0 to n. So the identity holds for all n greater than or equal to 1. Again, because we showed that assuming that it works for n also implies that it works for n plus 1. Like, we showed that every domino forever is close to the previous one, and 1 implies 2, 2 implies 3, on and on. Okay, so that there's like a little bit of sloppiness in there, but it's fairly good. Proof by Andrews. Let's see exactly how does he write it. Hey, how's it going, Leo Lectures? I'm doing good. I saw that you have that cool ZFC video, like something about like don't worry about choice. Don't worry about the axiom of choice. It looks really cool. I look forward to watching that soon. How's it going? It's going well for me. A lot of stuff going on right now. I'm fairly busy these days. A lot of really cool stuff happening that I could talk about another time. All right, so he starts out with a remark. Summation aj from j equals 0 to n minus 1 is shorthand for a naught plus a1 plus a2 plus ... a n minus 1. Okay, so he is just giving like a little I think he's just defining the summation symbol here. That's interesting. Yeah. I think he's just defining the summation symbol. He's not planning on using a just to like rewrite this. I think what he's doing is showing, by the way, if you haven't seen this before, this symbol means sum many terms. That's it. That's neat. I mean, I don't know. I think his audience should already know that by now, but yeah, I don't know. Okay, so he says, again, we proceed by mathematical induction. Of course, I'm going to use a few little shorthands like math parentheses L, but for the most part, I want to try to write this as close as possible, but we're going to take a few shortcuts. If n equals 1, then summation from j equals 0 to n minus 1. Oh, no, he wrote 1 minus 1 x to the j equals x0 equals 1. And x minus 1 divided by x minus 1 equals 1. Thus, the theorem for n equal 1. Assuming that the summation xj equals x to the k minus 1 divided by x minus 1 from j equals 0 to some number k minus 1, we find that from j equals 0 to, yeah, he does write it out explicitly as well, like I did briefly. From j equals 0 to k plus 1 minus 1, x to the j equals summation j equals 0 to, okay, yeah, he skips this step in between. Yeah, I like this. I think it works. J equals 0 to k minus 1 x to the j plus x to the k equals x to the k minus 1 divided by x minus 1 plus x to the k. Then he has his new line. And he does the exact same x to the k minus 1 plus x to the k plus 1. Oops. All right, this looks wrong. All right, so x to the k minus 1, the number, plus x to the k plus 1 minus x to the k over x minus 1. I'm just writing this down kind of verbatim, turning off my brain a little bit. I'm not like following and checking myself that the steps are working out, because I've already done this and it's pretty similar. So yeah, all right, there we go. X to the k plus 1 minus 1, it's basically the exact same thing, but I just want to write out his mathematical writing style. Hence, condition Hence, condition 2 is fulfilled, and we have established the theorem. He writes a little square, and for what it's worth, I think it's neat to know that he right indents the square. Cool. All right. So basically the exact same thing. I got the exact same proof. I like his phrasing a little bit more. The only place that I don't love, that I don't do myself when I'm writing these proofs, is like he swaps to k instead of n, just to make it clear that we are assuming the mathematical, that we're assuming the inductive hypothesis for some k greater than or equal to 1. And he wants to try to avoid the confusion between n and k. It's not really necessary. Like, you can just write out the formula with n plus 1. I don't know. I think it's like ever so slightly unnecessary, and like other books wouldn't make that distinction between k and n. So I didn't do that part. I also don't like that he didn't call out the fact that x is not equal to 1. And that is part of the statement of the theorem. And it's necessary if x is any real number other than 1. So he never uses and like refers to that fact in any of these steps. So I would have just said, thus the theorem is true for n equals 1. Or no, I would have said x minus 1 divided by x minus 1 is equal to 1 because x is not equal to 1 in the theorem. Like, I just would have added that in there. He never uses or explicitly calls out that requirement in the theorem statement. So, just ever so slightly different. All right, cool. So there is a proof, 2 different versions of the same proof. I'm worried about it being a video for no one. Those who know enough for it might know everything I talk about, and those who know less might find it incomprehensible. I'm in the exact same boat as you, man. Like, I'm trying to strike that balance, because, like, if I'm just doing math for myself, I would not be writing out this proof. But it is good practice as well, and so, like, I think your audience is out there, because I'm very interested in that video, and I do look forward to watching it, but it's going to take some time from my experience doing YouTube stuff in the past. It's going to take some time for you to find your audience. I hope I can help a little bit. Everybody, go follow Leo Lectures. He's got 1 lecture up, I believe, so far on how the axiom of choice is not as controversial as it sounds. So that sounds super cool. Yeah, I look forward to watching it. I'll let you know what I think. I'll comment whenever I watch it. Reminder to anybody watching this, leave a comment below. Let me know that you enjoy this as well. All right, so we accomplished our first goal. Our first goal was do the proof of 1, 2, and understand it. I think we got 2 different proofs. My own hobbyist proof and then a professional proof. Now, we're going to copy the proof just verbatim. I'm walking from the beginning of the step of the journey and from the end of the journey, and we're going to meet in the middle, and eventually we're going to understand what we're writing down. But, yeah. The proof of the thing that we're shooting for this week is the fundamental theorem of arithmetic. Let's just write it out verbatim and just get some muscle memory on how this proof goes. In fact, muscle memory, let's actually rewrite it. I'm not going to copy it. I could copy paste it, but let's get some muscle memory, including the shorthand, FTA. Oops. For each integer n greater than 1, dang it. For each integer greater than 1, there exist primes. P1 less than or equal to P2 less than or equal to P3 ... less than or equal to PR such that n equals P1, P2, dot 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 PR. He then has a semicolon right there, which is cool, and then says this factorization is unique. Okay, I should say this is Andrew's statement of the fundamental theorem of arithmetic, FTA, henceforth. Okay, so proof by Andrews. Let's get this. Our first goal is to prove that each integer has at least one prime factorization. Note that this table has such a factorization. Note that such a factorization exists for all n between 2 and 12. Now, let us now assume that each integer can be factored, each integer m greater than 1 and less than or equal to k can be factored into primes. Okay, so it looks like we've got a proof by induction coming up. He shows a table of base cases and then makes an assumption that any integer up to k can be factored after having some base cases. So that's cool. Here's a takeaway for me. Takeaway number one, as the math hobbyist, takeaway one, I didn't know this, but it is by induction. Like, that can be how you remember the proof of FTA is by induction. And you can stow that away in your memory, and you don't need to remember all the details at some point. And if somebody asks you on the street, prove FTA, you can say, I can try. Give me a pad of paper and a pencil, and I know it's by induction, and I'll try to figure it out. So that's my takeaway for today. By induction, which is cool because I just showed it mathematical induction. All right, so let me write that out. Our first goal is to prove that each integer has at least one prime factorization. Okay, now that I reword that and say it again, I notice first goal. He really calls out first goal is prove that each integer has at least one. So first, he proves that there exists a prime factorization. Then, a second goal is that it's unique. In his statement here, it's like, there's goal one, prove that there exists one, and then goal two, this factorization is unique. So, that's another takeaway. Existence is by induction. I don't know how he proves uniqueness yet. Cool. That's great. First goal is to prove that each integer has at least one prime factorization. Note that such a factorization exists for all n. He writes this for all n parentheses 2 less than or equal to n less than or equal to 12. I'm going to rewrite that slightly. I don't like that notation. And this is just notation again. So it doesn't matter that much. But I would say for all 2 less than or equal to n less than or equal to 12. And then he has this table. Table 2, 1. And I have a question about this table that I will think out loud about in a second here. And you might already see what my question is about to be. N from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So he shows 12 base cases. All right, so 1, the theorem doesn't apply. He uses a dash to say that. 2 is 2. 3 is 3. Yeah, we can do this. 2 times 2. This one's 5. This one's 2 times 3. I don't have to look at the table. I know how these factor. 2 times 2 times 2. 3 times 3. 2 times 5. 11. And then this is 2 times 2 times 3. Okay. So I wrote that, and now I'm looking at the table again, and now I see that he rewrites each of these. Okay. I see why. 2 times 5 equals 5 times 2, and then 2 times 2 times 3 equals 2 times 3 times 2 equals 3 times 2 times 2. I find that ever so slightly interesting. Oh yeah, Leo lectures. The ZFC axioms versus assumptions video might be more comprehensible. Talks about cryptography some. That sounds really great. I look forward to watching those. Yeah, I forgot. You do have 2 videos up so far. I'll check those out. Okay, so my question now as takeaways is it important to show 12 base cases? Question that I'm trying to be an active reader right now as I'm reading this proof. I'm trying to actively think and pause and reflect as I'm reading the proof. Let's pause right here before I read any more. Is 12 necessary? Or I think it's just illustrative. I think he's doing the exact same thing that I did earlier when I proved this other fact, just to illustrate and give some examples and some evidence that this is true. I showed a few cases, but you only need the first one. I just showed more just to get some evidence that this thing is true. I think he's doing the same, but that's a question. We'll find out. I think it's just illustrative. Now, a takeaway that he's doing is he is rewriting these two as like P1, P2, in this case, also equals P2 times P1, but the uniqueness... So, like, it seems like he's showing that this is not unique. There are 2 factorizations, but uniqueness in his statement comes from the fact that these primes have to be ordered. Right? From the ordering. So, 5 times 2 would not be a factorization, according to the way that the theorem was stated. Yeah. Okay, so that's a cool little interesting takeaway, and just thinking about how he is presenting this information. I like it. I think all that makes sense. All right, so let's continue. Note that such a factorization exists for all n between 2 and 12. Continuing, let us now assume that each integer 1 less than m less than or equal to k can be factored Okay, so here's where my notation is breaking down compared to his style, because he writes for that each integer m, parentheses 1, m greater than 1 less than or equal to k can be factored into primes. He's like kind of quickly defining two different integers, and he's using his math style that k is always like the inductive hypothesis number. The inductive hypothesis case. I don't know. Yeah, that he's introducing two different integers and two different variables there in one sentence. Yeah, that's cool. Interesting. I like it. Each integer m greater than 1 less than or equal to k can be factored into primes. Now, either k plus 1 is prime or it is not. Oh, one more thing. Technically speaking, throughout this entire book, I'm pretty confident Andrews always uses strong induction. Strong induction assumes the inductive hypothesis for every number between the base case and your hypothesis. Weak induction, like quote-unquote standard induction, only assumes it for one number, k, whereas strong induction assumes the statement for every integer between your base case and k. It's slightly different, and I think you can prove strong induction from weak induction, but it doesn't matter. You can just define induction this way, but I wanted to call that out, that most books will make that distinction, and the other books that I have on this do make that distinction. But yeah, so maybe that's another takeaway. Does this require strong induction? Strong mathematical induction? Cool. So now either k plus 1 is prime or it is not. Let's continue. If it is prime, then it's prime factorization consists of just the prime itself. If it is not prime, then k plus 1 equals ab. Okay. Cool. Okay, so this is going to stick in my memory. Like, in my memory and my takeaways, I see that this is a construction similar to Euclid's construction of multiplying a bunch of primes together and then adding 1. In fact, it is also adding 1 to the number that you... Oh, wait, no. What am I talking about? What am I talking about? I was thinking that k plus 1, like, where's the plus 1 coming from? But no, we're looking at the next case. We assumed that the theorem is true for k, and now we're seeing what happens for the next number. So I take all of that back. This is not an interesting takeaway. We are just saying the definition of not prime means that the number can be factored. Never mind. K plus 1 is the multiplication of two numbers where 1 is less than a, less than k plus 1, and 1 is less than b is less than k plus 1. Since 1 less than a less than or equal to k, okay, yeah. Since if a is strictly less than k plus 1, then a could be equal to k. Like, rewriting that first inequality as a second, or the second inequality follows from the first, that is. And likewise for b. Both a and b, nice, okay, have prime oh wait, no. He's using an S here. A has a prime factorization and B has a prime factorization. Okay, he uses primes. I don't like the primes. Prime. Yeah, anyways. P1 prime, P2 prime, ... PT prime. Therefore, k plus 1 equals P1, P2, ... PS. So that's A, and then multiplied by B, P1 prime, P2 prime, ... PT prime. Hence, k plus 1 has a prime factorization. Thus, we have established, oops, what did I do? Thus we have established by mathematical induction that every integer greater than 1, what time is it? I have to, hey Ben, how's it going, man? How are you? That every integer greater than 1 has a prime factorization. Boom! Okay, this is super cool. Let's pause and reflect. Because next he's going to do uniqueness. But let's pause and reflect for a second, because there's like some really cool takeaways for me. We started out this stream today saying that these were our goals. I wanted to understand the proof of the first theorem in our roadmap for this week, and then I'm going to rote copy. Maybe I won't understand everything about the proof of our goal, Theorem 2.5. We're going to meet in the middle at some point, you know? At some point, we'll stop rote memorizing and we'll start understanding every theorem in between. But so far, we can understand everything for the first half of this Theorem 2.5, the fundamental theorem of arithmetic, FTA. We can understand existence without anything more than mathematical induction. Strong mathematical induction. That was necessary. So in math, we often have these theorems where first you prove existence and then you prove uniqueness. So my little summary, my takeaway for FTA is that you prove existence and uniqueness. And for existence, all you need is strong induction. I'm going to try to remember that and commit that to my memory. If somebody on the street asks me, prove FTA, I say you prove existence by strong induction. Was there anything else that was necessary? I mean, really the definitions, but you always assume definitions, like whenever you talk about a strategy on a proof. Yeah, it didn't require anything other than what we learned in the very first section. The very first section of this book is on mathematical induction. Again, Andrews calls mathematical induction this property where you assume the hypothesis for every number up to k. In other books, so he just calls this induction, but other books will call that strong induction. So I'm going to commit it to my memory as you need strong induction, and that's it. So he could have put half, at least half. We'll see what happens in the second half, but he could have put existence of a prime factorization as an exercise in section 1. That's a really cool, that's a cool takeaway for me right now. And I don't think I would have seen that unless I was working in this way of like, start from the beginning, also rote memorize the end. Like while rote memorizing and just copying and assuming like I'm not going to understand everything, I was pleasantly surprised that, like, oh, I think that we can all follow that just from, like, the only thing that it requires is, mathematical, like, strong induction. That's cool. Okay. Another takeaway was that he also, as far as I can tell, he also likes to give several examples just to illustrate like what this theorem is saying. That's exactly what I did as well, and I wasn't sure if that was good pedagogy or style or not, but Andrews does the same thing. It's nice to have a few examples just to see what is this theorem claiming. Um, but like here he says in the proof, note that such a factorization exists for all n between 2 and 12. In my mind, I was just like, why 12? Like, I don't think that that's going to be necessary. I think he's just saying, like, here's a few examples. So 12, like, that was a takeaway. Like, I was like, do we need 12? Is somehow 12 going to be important? I don't think so. That's cool. So, yeah, I have a few takeaways here that are really neat. Another takeaway that I've said several times now is I really like this notation. And I think that's just going to stick in my head better. Whereas other books I've seen doing something like this. And it's equivalent. It's just that in this case, each PI is unique. And P1 specifically is 2. P2 is 3. And they're strictly ordered. P1 less than P2, less than strictly. I don't know why. I just think that that's a cooler. This may be more intuitive. It's like you write down a number as like 2 squared times 3 times 5 or something, whereas in Andrew's notation, he allows just like 2 times 2 times 3 or something. It's subtle, but I don't know why I like the way Andrews wrote that more than what I've seen before. All right, uniqueness. Let's continue. What do we got here? Now he says, to complete the theorem, we must establish uniqueness of factorization. Cool. To complete the theorem, we must establish uniqueness of factorization. Again, we proceed by... Okay, all right, we're getting somewhere. Again, we proceed by mathematical induction. Neat. So we are just showing how powerful and how often used mathematical induction is as a strategy. So again, we proceed by mathematical induction, but this is a separate proof, the proof of uniqueness. Okay, our table also tells us that the factorization of each n less than or equal to 12 is unique. assume that each integer m greater than 1, less than or equal to k. Again, we're establishing a inductive hypothesis. We're assuming strong induction between 2 and up to some number k. Assume that each integer m has a unique factorization up to some point. We knocked over the first domino, and so we know some number of dominoes are going to topple over. At least one of them will topple over. Let's pause the video, let's pause the camera, and try to analyze, like, as the dominoes are toppling, like, some number have toppled over. Can we prove that every domino from then on is close enough to the prior one such that that this theorem is true for all integers? Alright, so assume unique factorization up to some number. Suppose that k plus 1 has... Okay, here we go. Suppose that k plus 1 has the 2 prime cool. Pause for a second. He's going to write out some some notation and just introduce some variables and whatnot for the 2 prime factorizations. But I want to stow away in my head, for next time somebody asks me how to prove this, existence is done by induction. Uniqueness is induction plus contradiction. If I understand correctly, that is what that sentence is doing. We are going to prove a contradiction because he just said, suppose that this new number has 2 prime factorizations. We're going to do a bunch of steps and then say, this is crazy. This is absurd. Impossible. Your assumption was wrong. That's what a proof by contradiction is. And now I just wanted to mention that because we haven't seen a proof by contradiction yet. If we're working forward in the land of proofs. It's not hard. I briefly mentioned it yesterday, but we haven't seen a lot of examples yet of proofs by contradiction. But it looks like that's where we're going. So, suppose that k plus 1 has the 2 prime factorizations. K plus 1 equals p1, p2, ... pu, and p1 prime, p2 prime, ... pv prime. Okay, I'm going to pause and I'm going to rewrite what he's using. His notation I don't like because... Okay, so he's using p everywhere to refer to primes. I think that in number theory, L is a very commonly used variable to mean prime. I think L is very common. P is like the best. L is very, very common, and so I'm tempted to use L, but if I were writing this introduction to proofs and introduction to number theory, I would just use Q, PQ. Like, right? I think that's going to be nicer notation. I think that this is way better personally than P prime, because like then we also have this like weird overloading of the term prime. It's like prime prime, double prime, extra prime, the primogen. So I don't like it. I just don't like it. I'm going to switch to my notation henceforth, and working this into my muscle memory and trying to memorize this proof and be able to recite it on the street. This is going to be easier for my visual memory or whatever. K plus 1 is P1, P2, dot, 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 PU. I don't like U there either, but whatever. Q1, Q2, dot, 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 QV. I would use N and M, I feel. Oh, well, no, he's already used N and M. I don't know. Doesn't matter. Who cares? U and V. I don't like U and V. I'd rather just like alpha or A and B or N and M. I don't know. Whatever. It doesn't matter. Does not matter. Yeah. What I don't like is all right, this is too meta. Let's just move on. All right. Suppose, for the sake of contradiction, that the next number, k plus 1, has 2 prime factorizations. And we're going to see that that's stupid. Where P1 less than or equal to P2, dot, dot, dot,